Okay, thank you everyone for coming, and thanks to Black Hole for giving me this opportunity. They work really hard. So today I will be talking about tilings and the search for elusive Einstein. Okay, so this is not the Einstein that we know and love, who's a great physicist, mathematician, scientist, and thinker. Einstein in German means a single stone. Ein means single, and Stein means stone. And Germans have a habit of just putting words together, there has been a search for this thing called Einstein. So let me start with some animation. So in one way, I'm reasonably prepared for this lecture, but in another way, I'm really not, because you'll realize, I was working more on my animations, and so, didn't have enough time to make notes. But that's okay. If you want to understand tilings, perhaps the simplest example is this, right? That you have a red and a blue tile, and you have some kind of a rule, it says that you can't have two same colored tiles together, right? And, you just look at your bathroom and you realize what a tiling is. So, and the goal for mathematicians in a tiling is that they want to cover the entire Euclidean plane. So there should be no gaps and no overlaps. All right? And the set of tiles that you use is supposed to be finite. Okay? You have infinitely many copies of them. Right? But, it's no fun to, cover the entire plane with infinite. You could just do whatever you want and just introduce new tiles. So this is perhaps the first tiling that we're all familiar with, and this animation should convince you that it is possible to tile the entire plane. You don't have to really see it, right? So this is an example of a tiling. Here's a slightly more interesting tiling, right, within hexagon, and you all have seen it in your bathrooms and all over the place. Actually, this hexagonal tiling is quite spectacular. If you understand hexagons, you can understand a lot of things, including some major theorems in economics, and they all have to do with this hexagon. I could talk about a hexagon for, days, and, it wouldn't stop. And this convinces you that this is a tiling also. So people are more interested in something fancier. So let me show you another one. आप कह रहे थे ना पेंटागन से नहीं बनता. This is a pentagon, right? And this is this is a hard animation to make, actually. All right, and see what's happening. It should convince you that I can cover the entire thing. Yeah. So
these are not regular pentagons.
Yeah, these are not regular pentagons. If you actually look at this is pretty nice. It's actually based on a hexagon, and you've just divided the hexagon into pentagons. So there's some kind of cheating going on there, right? Okay, but it's fascinating if you look at it. You realize that these are hexagons, but you see that these are hexagons also. Okay, so and then you have these four different colored things, and that pattern is repeating also. All right, so this tiling is very, very popular in Cairo. It's found there in restaurants everywhere. So it is called the Cairo tiling, and you can just sit there and every time you think, oh, it's a different tiling, right? So it's very fancy, very nice, right? So this is a nicer tiling, all right? Okay. But these tilings are boring for mathematicians, all right? Because they're repetitive. The pattern repeats. So in some sense, there's this thing which I'm just copying again and again and again. It's really like a rectangle, okay? I could take, I could put a rectangular grid on it and just redesign the tiles and make them square. So these are called periodic tilings, all right? And, well, they are exciting, but they're not that exciting for mathematicians. So here's an interesting tiling, okay? I didn't have time to really programmed the first attempt in this direction. It was actually made by Johannes Kepler, the great astronomer, who gave us Kepler's laws. He was trying to create an aperiodic tiling. And if you've seen my abstract, there's a picture of a part of that tiling in it. And it has pentagons, and it has dodecagons, and it has some monsters, which are strange tiles, two overlapping, what do you call it? Tengons, two overlapping tengons. I don't want to say that word, right? So he was able to create aperiodic tilings. But what happened is people later realized that you could also use his tiles to create a periodic tiling, okay? So if you just put them in another way, they just become boring. He was just putting them in an interesting way, all right? Here is a wonderful tiling, and I love this. It's actually based on the triangle. The only reason I put a rectangle, I've put another thing upside down on it so that it looks aesthetically slightly more beautiful. So what you do is you have a triangle, and what you realize is that this is a 1x2 triangle. And what you can do is you can cut this, 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 and all of these 5 are 1x2 ratio triangles. Of course, they're smaller, right? But they're all similar to the original triangle, all right? And this was found by John Conway, who recently died, okay? Once you realize that you can take an object and you can cut it up into objects which look like the original object, you have something interesting, because now you just repeat. You scale, you repeat, okay? It convinces you that this is a tiling, all right? It's pretty neat, okay? Of course, now most of the tiles are out of here, right? So this is fascinating tiling by John Conway. So I can, if you don't understand this comment, don't worry about it. But just for mathematically minded people, the line segments are pointing in directions, different directions in the plane. So there's different angles that are being formed. So what you can do is you can draw the circle and say, well, this angle was formed, this angle was formed, right? You can do that, okay? So you can ask which angles are formed by the Conway tiling, And you realize you can never cover the circle because it's uncountable. And you're going to only repeat this countably many times. But what you get is a dense set on the circle. So you can come arbitrarily close to any direction that you want. This is a line segment arbitrarily close to the direction that you want to point. So that's a very, very nice property. It's a fascinating object. And okay, so here's a little problem for you, the exercise that you can take home. So what Conway did was, he did it for one ratio 2 triangle, right? He cut it up into, I think, 5, right? Is it 5? Yeah, it's 5 similar triangles, smaller like that. Well, can you do this for other ratio triangles? These both sides are integers. So for example, what about a 2x3, right triangle? A leg is 2 and the other leg is 3. Can you cut this up into finitely many similar triangles? Okay, if you can, you will have a Conway style tiling. And it's not a difficult problem. You can start with 2x3 and then you can try to generalize it. It's a very nice question. Okay. So let's see what we have. Oh, this tiling is aperiodic. Yeah, this tiling is aperiodic. But let's notice one thing, that although the tiling is aperiodic, the tiles are not. What I can do is I can just take another one, 1x2. This is 2, this is 1. And now I have a rectangle. And now I can just copy it. Just like as if I was making a rectangular tiling. Okay? So Conway's tiling is aperiodic, right? But the tiles are not inherently aperiodic. Okay? So so the question is that you can take tiles from which you can have periodic tilings and you can have aperiodic. Conway's triangle is an example of that, right? But the question is, are there any tiles for which you only have aperiodic tilings? Okay, where it is impossible to, just keep copying them. You have to do something interesting all the time. All right, so that was a fundamentally open problem. And the answer of that question, guess, came from where? It came from computer science. Okay, actually people showed that if every set of tiles for which you have tilings has a periodic tiling, then a certain problem was computable. All right, and then somebody proved that it's not computable. All right, so that showed us that there must be inherently aperiodic tiles. All right, and the first proof that came was in, I think, Wang and Berger, about 10 years apart. If you put their work together, you get the theorem. There was over 20,000 tiles. Nobody could look at them. They were described mathematically. We had no intuition. And we knew that these tiles will aperiodically tile the plane, but never periodically. Okay? There was a proof, but... So people got interested in this, right? So they started saying, well, can we manage to find tiles which we can actually look at, like 10 or 7 or 3 or 4, right? So people started bringing that 20,000 number down. And then it was somewhere in hundreds. And then there was a physicist, Roger Penrose, who came up with 2 tiles. Who came up with 2 tiles that were aperiodic, only 2 tiles. All right, okay, so let me show you Penrose's tiling. And why does this... Okay, so here is Penrose's tiling. Okay, so here I'm showing you how you will go about doing this. You have only 2 kinds of tiles. Okay, this is one, all right, sort of a long rhombus, and the other one is another rhombus, right? And these are based on the golden ratio. If you people know about it, the golden ratio is lurking all over the place. And what, a nice proof is you cut them in half, and then you have a substitution rule, just like you had for Conway's tiling. So here, what you do is you scale, and then you substitute. Okay, and then you scale, and then you have a substitution rule. Okay, and you start getting these, these beautiful patterns. Okay, and this one has a 5-fold symmetry. Okay, but it doesn't have a translational symmetry. Okay, right? So that's Conway's tiling. It just keeps getting more and more complicated. Okay, I should have something. Okay, here's another of Conway's tiling. Okay, this is the original one, but I'm not showing each substitution, just showing you how complicated it gets. Okay, because this would have taken a lot of time if I would have shown you the other way. So it does get more and more intricate and beautiful, I think. It's a fantastic tiling. Okay. Here I have to take a little intermezzo. So the Penrose tilings were discovered, I think, in the 1960s, 2 tiles, 2 aperiodic tiles. But later on people realized, and I think you were talking about it before the talk started, that Penrose tiling was found in 15th century mosque in Isfahan in Iran, and also I think in Uzbekistan or something like that. And so these people knew about Penrose tilings. They just didn't bother to prove that they could cover the entire plane. Penrose proved it. Okay, so but the tilings were known to people, 300-400 years ago, right? So after Penrose, I think, this is also a Penrose tiling, okay, and you can see how complicated it gets. Okay, now I want to ask the mathematicians here a question. So the animations I'm showing you, they're showing you that I can cover larger and larger area. But if you see, when I cover larger and larger area, it is like I have to change everything from the beginning, right? Even the center changes its color, right? So I can convince you that I can cover arbitrary large areas. Does that mean I can cover the entire plane? Okay, so if I have a tiling with which I can cover arbitrary large areas, does that mean I can cover the infinite plane? Okay, and,
Probably not. I don't think so.
It is true, but it's not trivial to prove. There's a deep combinatorial reason that is there, but it happens to be true. But you're right that it's not something you should take without a proof, right?
But can you give us an intuition as to why? Because how can we reach, for example, if at every step all the tilings change, then how can we reach the point of infinity?
Okay. Can we do it at the end of the talk? Because it will get technical right now, and I want to keep it very simple, right? So after Penrose, the search was on for a single tile, okay, which was aperiodic, with which you could cover the entire plane, but you would never repeat yourself, right? So that was what the search was on. And let me sort of show you what kind of previous examples people found. Oh, I lost it. Okay, so sorry about that. I seem to have lost the page. So people were able to come up with one tile which was aperiodic, but the problem was it was a disconnected tile. Okay, so mathematicians have no problem imagining a disconnected tile. You move one tile and the other moves with it, right? That's like that for them. But physically, nobody would accept that as a nice solution. There were also people who were able to come up with two tiles, said that one was a scaled copy of the other one. Okay, all right. So it was like 1.7 tiles or something, because they both were scalars, scaled copies of each other. So these were the solutions, but nobody was able to find the Einstein, right? Till about, I think, 2 months ago or something. I don't know what the exact date when the paper was published. Okay, and it's amazing that you search at Wikipedia page for aperiodic tilings, all right, and all they talk about is this. It's all over the place now. So it's a huge result. Okay. All right. So finally, people were able to find the Einstein, and all right. Some people say it's a hat. All right, and other people say that it's a shirt. If you turn it around like this. All right, and people have found turtles in it. People have found all kinds of artists. You could take some of these home and give it to your kids and tell them to make something interesting from this from this single tile. It's really a beautiful one. So the rest of my talk is going to be an argument with a lot of hand waving to convince you that with the Einstein, with this tile, with the hat, you can actually cover the arbitrary large areas of the plane. Well, if you believe that theorem, which means it is a tile that entiles the entire plane. So let's look at it. So the proof sort of goes like this. Okay, before I do that, maybe we should look at this a bit more carefully. I was trying to do this on my notepad. If you just concentrate on one of them, all right, let's take which one? This green shirt, right? Okay, it's actually made out of one, okay, pentagon, and it's made out of second pentagon, a third one, and a fourth one. Okay, it's made out of four pentagons, all right, and those pentagons are sort of extracted out of hexagons, right? So I don't know how they thought of this pattern, and it has 13 sides, which is also sort of curious, why 13? That's a prime number. Does prime number, do they have anything to do with it, right? So this is the Einstein, right? So I'm going to try to convince you that you can cover the entire plane. With all the work I've done, I'm convinced we can. So I don't know if you would get convinced. Okay. All right. So here is a bunch of Einsteins. Sorry about my graphics aren't really working perfectly, and so that. So this is what we can do. We can, how many have I taken here? I've taken 8 of them, all right? And I can make this particular shape, right? Putting 8 together, this you can just play with them and you can make this shape. This shape is how they made this shape, and why would you make this shape? I have no idea, right? But if I tell you you can make this shape, then you can do that, right? All right, so this is something which is called H8. Okay, H stands for a hat, and it has 8 hats in it. All right, now let's see if we can go further. And what you can do is you can make another thing which is called H7. All right, which is even easier than H8. One of the hats has been thrown out from the side.
Isn't this
1, 2, 3, 4, 5, 6, 7. Oh, yes.
the next animation?
Oops. Okay. All right. So, yeah, there was a mistake. I mean, for some reason, I've used the same file. So that was a H8 that I showed you. This is an H7. This is an H7. And these are a bunch of H8s that I have put together, right? Okay. And this is crazy. This is amazing. But what you can do is you can take, I don't know how many H8s I have taken, 1, 2, 3, 4, 5, and one of these H7s, and you can put them together like this. Okay, so how many H8s are there? 1, 2, 3, 4, 5, 6, 7, right? And this thing is similar to H7. Okay, this is just an H7 blown up. Okay, how did they figure this out? Okay, and oh, by the way, the paper is 80 pages, over 80 pages. Okay, it's beautifully written. It's, obviously they've spent time on it, and it has 3 proofs that it covers the entire plane. And this is the simplest to explain, but perhaps the hardest to come up with. Who would think of doing something like this? All right, so, okay. I think that is probably my last animation. All right, so let's look at this again, just for fun. And why wasn't there a 12 there? Okay, all right, okay. So let me use the chalkboard a little bit. Okay. So in this case, what I have is 1, 2, 3, 4, 5, 6. 6 H8s plus 1 H7 is equal to a large H7. Okay? All right. And in this picture, if you just throw away this thing, right? Okay? Then you realize that 1, 2, 3, 4, 5, 5 H7, H8 and 1 H7 is actually an H8. Okay? So 5 H8 plus 1 H7 is equal to a large H8. Okay? All right?
Which one is removed?
Oh, yeah, I should have made two animations, okay? And I should have also made an animation blowing up this thing and, it actually showing you. So this one is omitted,
Okay.
okay? And then this figure is actually just a blown up copy of an H8,
Okay.
okay? All right? And if you don't throw this away, this is just a blown up copy of this thing. Okay, all right.
For the first equation, are we sure that it really becomes like H7, a larger one?
Yeah. I mean,
Because I have some doubt looking at it.
well, I have lots of doubts, but I've checked it, right? I mean, I had, just the fact that these things fit together was remarkable to me. I didn't think they would fit together. It took me a lot of time, yeah. So there should be another animation showing that.
All right.
All right. So once you have these two things, you're done. Start with the H8, right? Blow it up, okay, and fill it with H8s and H7s. Then blow each one of them up and fill it with H8s and H7. And then blow each one of them up and keep doing that. All right? And you start covering arbitrary large areas of the plane. All right? And modulo that theorem, we then can cover the entire plane. Now, they do have also a proof of the fact that this tile is aperiodic. Now, those proofs are difficult. In mathematics, proofs that you cannot do something are far harder than proofs that you can do something. Because proofs in which you say, I can do this, you just show a method of doing it. Here they've actually shown an algorithm, right? I was able to write a program based on that. So they've shown an algorithm, just like I was showing you those animations of Penrose tiling getting bigger and bigger, right? But how do I know Penrose tilings do not periodically cover the plane? How do I prove that? Because remember, the period could be very large, so how can I be sure? So that requires complicated arguments, complicated mathematical arguments. And in their case, they say that their proof is computer assisted. Now, because it has a lot of cases. I was going through their paper, and it was just pages and pages of cases that they are considering. So that's what I have to say about the Einstein. And the idea was, just to introduce you to some, interesting subject. If you search the internet for, aperiodic tilings or something like that, you can spend weeks just looking at those things. They're so beautiful, so intricate, so amazing, and the history is so nice that, you can really get hooked onto it. Okay, but now I want to end with one question. Is this the Einstein we're looking for? I mean, have we found the Einstein? Okay, even if you found it, there are a few interesting questions. Are there others? So that's an interesting question. But the question is this the Einstein? Is this a Einstein? Yeah?
I mean, why isn't it? Because as you told, it covers an arbitrary infinite plane. Then why can it be?
Okay, so it's got to do with how you define things. In this arbitrary covering, you will realize that one of the tiles, the dark green tiles, are flipped. They're a flipped copy of the original one. Okay? And over here also, all the center tiles, within each one of these H8s and H7s are flipped copies of it, right? So when I brought these tiles, I actually cheated, right? Because they seem symmetric from both sides, right? But when I go and buy bathroom tiles, I'll have to buy two kinds of tiles if I'm going to use the mirror image. Okay? So maybe there is a problem for you to work on. Maybe you can try to come up with a Einstein, the true Einstein, where you do not use a flipped version of the original tile. If you can do that, if I could do that, I'd probably give up my life for it, in an instant. So, but that's a wonderful problem to work on. And one of the authors of this paper, the major author of this paper, was not a professional mathematician. He was an amateur, and he was the one who found the Einstein. The other authors helped him prove things about it, right? So it's not like, you have to be a professional mathematician to work on these problems. You can just play with these things, and maybe, after a while, yeah.
So is there any मेरे दिन में लफ्ज़ नहीं आ रहा, इसमें कोई हमारे पास ज़बरदस्ती है कि इसकी इतनी साइड्स ही होनी चाहिए, like it has 13, can it have more than 13 or less than 13?
No bounds. You could have Einstein with 50,000 sides.
Then how do we check it? How do we know that it's an Einstein?
So look, mathematicians have ways of proving things, So for example, they were able to prove that a set of 20,000 odd tiles was aperiodic, right? So they have very powerful ways of thinking. They don't always have to examine things so closely. They can say very general statements. So it would be very difficult. If an Einstein exists on the one that we're looking for exists on like 80 vertices or something, I don't know how to think about it.
Then for it to be found by an amateur, it's like a 1 in a million chance.
Well, this one was.
Yeah.
This one was, It's, look, they say that you've got to be in it to win it. You can't be worried about failure. If you're interested in something, just think about it. Great work has been done by graduate students and, also amateur people. Yeah. Okay, so any questions?
Well, when we look at these 6H8 plus 1 H7 is equal to 1 large H7, so isn't it one kind of a pattern? Why do we call it aperiodic? Why not? I've heard the other term quasi-periodic. Isn't it quasi-periodic?
Yes, one should say they are quasi-periodic because even Penrose tiles have to do with quasi-crystals. There is a certain symmetry there. So for example, Penrose tiles have a rotational symmetry, five-fold rotational symmetry. Strictly speaking, when mathematicians say periodic, they mean translational symmetry, right? So if you go into the literature, you'll get bogged down with lots of definition. What is a semi-periodic tile? What is this kind? They have classified all kinds of properties that they want or don't want in them. Yeah.
Well, in one of the videos, I'm not a math graduate, but I'm interested in it. In one of the videos about Penrose tilings, I watched it long time ago, don't remember the exact details. But he says that there is a hidden pentagrade in it.
Yeah.
And if I can recall it, I think there were some, the ratios he was talking about, 72 and 36, which is the golden ratio.
Yeah.
And because it is an irrational number, that is a kind of layman's proof that it's never going to...
Yeah. So you saw Conway's tiling that I showed you, right? Yeah. What happens is if you have a ratio 1 and 2, right? and you look at this alpha, this slope alpha, this is not a rational multiple of, sorry. Okay, if you look at this, so let me just draw it here, right? If you look at this angle alpha, this is not a rational multiple of pi, okay? And that is why these things, because then things here get, go in that direction, right? Okay? So that's why they start filling the circle. If it was a rational multiple of pi, it will start repeating itself. Right? If you start adding rational multiples of pi, after a while they'll just keep on falling on the same place, right? Because once they become 2 pi, they'll come back and fall on the same place, right? So yeah, irrationality and relative irrationality has a lot to do with this. Yeah. And underlying there is always a certain kind of symmetry.
So if there is certain kind of symmetry and it is quasi-periodic, why do we call it uncomputable?
Oh, uncomputable? We don't call it uncomputable.
Roger Penrose actually tried to prove uncomputability through this Penrose tiling.
Well, yeah, Penrose is a tremendous physicist, but some of his ideas are, I can't understand them. His work on consciousness and all that, it's sort of beyond me. And, so, uncomputability theory is a well-developed theory in computer science, right? So.
Okay, and Sharyar actually asked a question. I'm also interested in that, so maybe after.
Oh, yeah, yes. Sharyar asked a question, maybe at the end, just when, that will be the last question.
I want to ask, if we assume that the infinite space is something like a square or a triangle, then the stars won't be able to fill it, or a circle. The stars won't be able to fill it. By saying that the space is a certain shape, then these stars won't be able to fill it.
Yeah, so for example, what you're saying is, what if my space is finite? It's a square, all right? And that's a fantastic question, okay? So here, let me give you a wonderful puzzle, and you can try to solve it at home. And the puzzle is this, that I have a square, right? Okay? And it's a unit square, perfect square, right? And I want to cut it into 4 pieces, okay? Such that when I put them together, it becomes a triangle. All right? So that's another cutting puzzle. In this case, where your pieces come from is a finite space, and where you are trying to put them in is also finite space. Right? So those are wonderful. These are called, there's a whole area in mathematics. People study all these kinds of problems. Right? Another beautiful question is that, suppose if I give you a very strange shape, which is called a simple polygon, right? And I give you another very strange shape, but they have, whose area is the same, okay? Is it possible to cut this up and put it in here together? Is it always possible? Okay?
Yes, if you cut it into small enough pieces.
Huh?
Yes, if you cut it up into small enough pieces.
You're allowed to do that in as many pieces as you want. But here's now my next question for you. So we have a cube, right? Okay, and we have what is this thing called? A tetrahedron? I think it's called a tetrahedron, right? Okay, and they have equal volume. All right, is it possible to cut the cube and make it into a tetrahedron?
Yes.
And the answer is no. Not in a billion pieces, not in a trillion pieces, not in finitely many pieces. You will have to make it infinitely, you'll have to get...
You have to get them into 2D shape.
You have to use limits. So the answer for a cube to tetrahedron is no. So why is the answer for a square to triangle? Yes. Okay, so somehow we don't understand something. Okay, and the proof of this thing that it's impossible is so beautiful. It's just amazing. So let me give you a hint of how it's proved. So let me ask you a simple question. Suppose if I have a square and a triangle, and this has area A1 and this has area A2, and A1 is not equal to A2. Can I cut this up and put it together like this?
No.
No, you cannot. What's the proof?
Area is conserved.
Area is conserved. Area is an invariant under cutting. When I cut something, the sum of the areas remains the same. Okay? So there was a student of Hilbert called Den. Okay? Remember I gave a talk and there was something called Den's lemma which I was, going gaga about. So he was the same Den. Okay? So what he did was he said that I'm going to define something called a Den invariant, and it is going to be invariant under cutting. It's going to be a conserved quantity. So he defined a Den invariant, and then he computed the Den invariant for this and the Den invariant for that, and they were different. And said the same argument that applies to volumes applies to Den invariants. Okay? So, mathematicians are wonderful people. Yeah. And eventually this proof boils down to irrationality of a number also.
Sir, is there a connection between the prime number of sides of the monotile? For example, if it was not prime, perhaps there is a way to disprove the aperiodicity, because if it's not a prime, then it can be, for example, divisible. It might be able to be converted into another shape that repeats, since it is not divisible. So that might be one of the ingredients of the aperiodicity.
Yeah, I mean, I feel that there's something special about primes, like 13, but to make connections from number theory to geometry is a very deep subject, I'm not good at either of them, so I'd refrain from commenting on that.
Are you aware of any proof, for example, that sets any kind of lower bound on the monotile? For example, like if we keep reducing the number of sides, then the shape gets simpler and simpler. There should come a time when it's so simple that aperiodicity is impossible. So has there a lower bound been established yet?
I am not aware of the literature, but I know that there are theorems like that. So please double check me, but people may have proved things like that. The Einstein, if it exists, could not be a convex object. Okay, could not be a convex polygon. It had to be non-convex, as this one is. So people have certain classifications of saying if there is a Einstein, then it must have this property or it can't have this property. So one has to read that literature to narrow the search if you're really looking for it. Because you may be looking for something which already has those properties which are not supposed to be there, right? So if one has to work seriously on it, then you have to read the literature. Yeah.
And have people search for aperiodic tiles in other dimensions as well, for example, 3 dimensions?
Absolutely. And things get really, really complicated because, in 3 dimensions you can visualize things, but what happens is the inside is hiding there, right? You can't view the inside of a 3-dimensional object, right? So even that becomes more complicated. For 4 dimensions, I think physicists have to step in.
तो मैं मैथमेटिक्स का टीचर हूँ, मगर सारा ये कुछ जो है मुझे लगता है कि ख़त्म हो जाता है मेरा मैथमेटिक्स। अच्छा सर, अभी आपने जैसे ये कहा कि क्यूब से पिरामिड में जाना मुश्किल है।
हाँ, टेट्राहेड्रन नामुमकिन है, मुश्किल।
ठीक है, मगर हम पिरामिड से क्यूब पे जा सकते हैं?
No, because if you can cut something and put it together into another thing, so then you can do the reverse. Huh?
मुझे एक एक्सपीरियंस हुआ इस तरह के मॉडल्स बना के कि मैंने 3 पिरामिड से एक क्यूब बना लिया तो मुझे बताइए कि क्या ये मेरे सिर्फ मॉडलिंग में कोई गैप होगा?
नहीं, आपने 3 पिरामिड में क्यूब बनाया ना, उसमें एक पिरामिड से एक टेट्राहेड्रन से एक क्यूब
नहीं नहीं, एक नहीं, बहुत सारे से मिला के।
हाँ
ये कि मसलन अगर मैं 2-3 जो है 3 इस तरह के टेट्राहेड्रन
हाँ,
ले लूं,
टेट्रा
वो नहीं, वो वाला जो उसके 3 बना के क्यूब में आ सकता हूँ।
हाँ, नहीं, एक सेकेंड,
कि अगर 3 टेट्राहेड्रन हो मेरे पास तो उससे मैं एक क्यूब बना सकता हूँ। और इस तरह से ये है कि एक क्यूब से क्या मैं 2-3 टेट्राहेड्रन बना सकता हूँ?
हाँ, उसमें जब आप स्पेसिफिक सवाल पूछेंगे तो आंसर कभी हाँ होता है, कभी नहीं होता, राइट? कुछ सिंपल केसेस में तो हो सकता होगा ना।
सिंपल सा एक
सो फॉर एग्जांपल, अगर मैं यहाँ पे सेंटर में एक पॉइंट रख के
जी,
और यहाँ से चीजें काटता जाऊँ
जी।
तो मुझे बहुत सारे पिरामिड्स मिल जाएंगे,
बिल्कुल बिल्कुल।
राइट? बट दैट्स नॉट द क्वेश्चन। इसमें सवाल ये है कि एक क्यूब है, उसको पिरामिड में कन्वर्ट
किया जा सकता है।
उसको टेट्राहेड्रन में, आप, मैं बार बार पिरामिड कह रहा
ठीक
हूँ,
है।
उसमें कन्वर्ट करना है विदाउट एडिंग और सब्ट्रैक्टिंग एनीथिंग।
अच्छा, बहुत फिर वाकई
या
difficult काम।
सर शहरयार प्राइम नंबर की बात कर रहे थे, रैशनल नंबर्स भी इसमें है। तो ये जो इलूसिव आइंस्टाइन है, इसमें मेरा ख्याल है वो इमेजिनरी नंबर भी इंक्लूड हो सकता है। दूसरा मेरे जहन में ये आ रहा था कि अभी तो हम यूक्लिडियन ज्योमेट्री की बात कर रहे हैं, तो 4th डायमेंशन को छोड़ें, अगर आप उसको कर्व्ड सरफेस पे देखें तो हो सकता है वो एपीरियोडिक ना हो सकता है किसी वो पीरियोडिक हो जाए, या
I would just like to ask you to look at MC Escher's drawings. उसकी बहुत सारी जो हैं वो tessellations पे based हैं, but also of the non-Euclidean geometries. So there is a concept of tilings, and some of those pictures are fascinating, and you know, he has a lot of pictures of non-Euclidean geometry में of tilings there. Yeah. So the concept does exist. लेकिन मुझसे तो प्लेन ही हैंडल नहीं होता। मैं
no, actually I don't do maths, but I do origami. Origami has lots of tessellations, and it actually gives you a lot of intuitive knowledge about it.
So if you're interested in origami, there is a wonderful mathematician, computer scientist. He's a very young guy at MIT. What's his name? अभी आ जाएगा। हाँ, he proves theorems about origami. Okay, and you know, there are just algorithms now that you can take any shape and you can give it to a computer, and the computer will tell you how to do that kind of origami for you. And it took years to prove that. Yeah.
अच्छा, इन डायग्राम्स की कोई प्रैक्टिकल इम्प्लीकेशन भी कहीं होती है?
All right. So mathematicians don't worry about these things. I mean, you know, you spend 50 years trying to find a style. I mean, to get what few pages of internet space. I mean, it's not really worth it, right? In that sense. But in the long run, they have tremendous applications. The mathematics that comes out of it. For example, origami, which seems like, you know, something which people do to entertain themselves, is immensely important in space science. You know, what you have to do is you have to fold your telescopes, you have to fold your materials, you have to solar panels and everything, and then you have to open them so that they open without, you know, any problems. And they're fascinating applications of it. I mean, many of now, आजकल तो Google Maps है, people are having accidents while looking at them, but हमारे ज़माने में we used to have those maps, right? Very strange maps. So once you opened them, it was so hard to put them together. In Japan, they use origami to make maps, which, you know, you pull, they open, and then you just do that, and they close. You know,
Yeah,
so
and Dr. Sarmad, a quasi-periodic crystal was also
crystals,
discovered,
yes,
which
yeah.
I'm not sure if they will discover something related to this as well.
Yeah.
See, Roxab, I just want to know why this remained elusive, because I think in Islamic architecture there was pretty apparent application of these styles. So why did Einstein remain so elusive?
Well, Penrose पेनरोज टाइल्स तो इस्फहान में मिले हैं ना, तो वो तो वहाँ पे थे, लेकिन इवन this tile has not been found so far in any architectural buildings or anything like that. So probably nobody got this idea, And if you think about it, in architectural tiling, if you're sophisticated, you typically want to use more than one tile for variation. Right? One tile is actually very boring if you think about it. I mean, in this, the exciting part is the flip tile, right? That gives it a little bit of flavor. Otherwise, it'll just be, you'll have to color it in one color and it'll be very boring. Yeah.
I do not have that much knowledge about the things because I just came in and that. But the thing which surprised me was that when you said that cube and that tetrahedral shape, they have the same volume, but they cannot fit inside each other. But on the converse, if I'm right, correct me if I'm wrong, that volume is conserved. I mean, there is a limited space which can be filled inside this room. And on the other side, when you go towards that 2D shape, and in that shape you can just fill out if both have same area. Why can't these two shapes having the same volume be fitted inside each other?
They can be fitted inside each other, except for here you have a limitation that you can only cut them. Okay, and you can only cut them finitely many times. Okay, that's a limitation. It's not like atta. Okay, you can just press it and push it together. That you will be able to do, right? It's not like water that will change its shape. It's a solid, and you have only a knife to cut them.
It's like that example which I used to hear, that a piece of paper cannot be folded cannot be folded multiple. There is a finite number to which it can be folded. After that, it is not possible.
Yeah, and that number is not very large.
That's number, yes, sir.
Yeah.
And secondly, I do not have that. Earlier told you I do not have that much background.
वो paper folding वाला तो I can convince you very easily of that. Using very elementary mathematics. Okay, this requires higher mathematics.
Because this will just trigger my thoughts, and I just want to ask this point that it is like limit approaches to zero. Mm-hmm. It is something like that which you are trying to tell me, that you can just cut a finite number, infinite pieces can fit inside it, because it is something like that.
Yeah, with infinite pieces, you can do it using calculus. Calculus people do that all the time. Sir. In fact, that's what they're doing when they compute the volumes of these.
Limit approaches to zero, yes.
Yeah,
sir.
They just take the limit and then they. So
that was clashing with me.
Yeah, but here the thing is finite. Here, with square and triangle, you can do it with just 4 pieces.
Thank you, sir.
Yeah. And you guys can work on this. I can send you the solution, or you can look for it on the internet. But it's much better to give it a try yourself for a while, before looking up.
Why people are looking for aperiodicity? Just simple.
It's what fascinates you, huh? जो भी आपको अच्छा लगे, जिसमें भी आपको मजा आए काम करने में, और जो भी चीज़ mysterious हो. It's like, why did we climb Mount Everest? Because it was there.
Because we are crazy.
No, because it was there, So if something, people can't find it, then mathematicians either want to prove that it doesn't exist, or they want to find it. That's the nature of the beast.
Yes, exactly. So I would like to respond to your question of applications of mathematics. Most of the mathematicians, they do mathematics for the intellectual lust. Okay, so there's it. You can read the Hardy book on Apology of Mathematics, a mathematician's apology.
Well, Conway has this quote which he says that it may not be obvious to non-mathematicians, but mathematics is an aesthetic subject almost entirely. It's almost entirely aesthetic.
And the question regarding Islamic geometry is that there is a basic pattern which we study in crystallographic groups, that you create a motif and you repeat it. But then there is something we look for, which we call fundamental parallelogram, that essentially fills the whole plane, and whatever happens in the fundamental parallelogram has to repeat, because the whole plane modulo of fundamental parallelogram is the same thing. So the motif that has to do within the motif, whatever happens over all the planes. So that is what we study in crystallographic groups. But how we can look for a fundamental region in this case?
Look, I've just found out about it, and I've prepared this talk. Okay, and most of my time went into making those animations.
They were lovely.
So I haven't really been able to deeply think about it, and probably I won't, because this is not my cup of tea. I do graph theory, algorithms, so.
The proof is computer generated?
No, the proof is a mathematical proof, but it's
okay.
computer assisted, because there were many, many cases they had to consider.
When we talk about Penrose, what is it called? The pentagrade.
Yeah.
So, for pentagrades, what they do is they start with one tile, and then they look at the neighboring tile, and if I think the edge that is parallel to it, so they make kind of a band, snake-shaped band, and those bands actually make those pentagrades. So, can we try with this?
Okay, so the substitution proofs, that the animations that I made, right, they're based on some things called substitutions, which is like you take a tile and you essentially, you take pieces of that thing and you fill them with, pieces which you know about. Those proofs came later. I think the Penrose proof was the way you're describing, looking at the neighborhood and then deciding what to do. And so these proofs are easier. But I think the proofs that you're telling are more natural and straightforward, although they may be harder. These substitutions, I mean, how did these guys came up with this H8, H7 substitution? It's bizarre, crazy. Once they've done it, it's very easy to check. But how did they thought of putting these? And it was crazy, because these things are rotated over there. It's really bizarre.
Can't we do the cube problem by saying that if we put the cube within that the tetrahedron, where was by putting it there and carving out the pieces that do not match, and then putting them in the pieces, then the empty void will fill it up eventually?
Yeah, so what you're describing is an algorithm, is a procedure that, you cut a piece, you put it in there, and then whatever.
No, you put the whole cube within it.
And then you cut the sides, whatever is sticking out, and then you keep repeating that. So the theorem that I've told you proves that you will never stop. You'll just keep doing that. There'll always be a little bit left, At some point, a physicist may think that you reach molecular levels and so you're done. There's nothing in there to do, but mathematicians will say, no, there's volume. So it'll be an infinite process, yeah. It's a good idea, though. Yeah. So it's a very nice idea.
Okay, so with the current technology that we have, artificial intelligence and the huge computer power, can't we just give computer this command and just he keeps on doing it until he finds?
There are automated proof systems. There are computer-assisted proofs. So, for example, the Kepler conjecture, which says that, the way to stack oranges is the way we do. That's the best way to stack oranges, right? It was proved, and it was then, there was a computer-assisted proof, and the proof was checked by computers. So that kind of thing can be done. But, I haven't seen a computer produce anything close to mathematics or anything like that.
Because as you said that how it's so bizarre that a person could think of it, I think that a computer could do much better if it's given correct commands of what to do. No?
I don't think so. But it's a big debate. Computers aren't very good at looking for proofs, I think.
Okay, and the last question, I may be repeating it. Einstein is a tile that that can not repeat itself, but can somehow make an arbitrary infinite space without cutting or
Yeah, yeah.
flipping.
So there'll be no overlaps, there will be no gaps left. And you'll cover the entire plane, but you will never be repeating yourself. Even if you wanted, you wouldn't be able to repeat yourself. If you try to repeat yourself, you'll just get stuck.
Repeating as in
Translation symmetry.
you just copy paste.
Copy paste, yeah.
Okay.
Yeah. Well, but not copy paste a short piece. It could be an arbitrary large piece. It could be very complicated.
That's why I keep coming back to this question of computability, because I am interested in consciousness. And Roger Penrose actually says that since this is non-computable, it means, and human beings have found a solution, so it means that human beings have a device which is non-computable, and hence consciousness is something which can't be simulated by artificial intelligence. This is the argument he makes. And Alam was asking, why are they interested in this aperiodicity? I think this is one reason, because we want to look for this unique human feature, because our existence, like human existence, is at a threat when we try to compare whether machines would overpower us or not.
Yeah, so look, one of the things is mathematical theorems are very precise, right? Whereas ideas like, I don't even know a proper definition of consciousness that I can understand. The only way I understand is through shared experience. I am as conscious, Sharia acts as if he were conscious, so he must be also. Other than that, I don't know what really it is. I stay away from these questions,
That's the way how mathematicians take consciousness.
Well, mathematicians wouldn't have anything to say about it. But the people work in multidisciplinary areas. That's fair enough. That's fine.
Mm-hmm.
There are mathematicians who work on mathematical biology. That's good. That's nice.
No, it's not the problem of consciousness. It's whether, is there anything which is non-computable? That's the question. And human beings, can they achieve what computers can't?
Okay.
That's the question.
There's a flaw, and let me just say there's a flaw in Roger Penrose's thinking. So suppose if I say that a problem is uncomputable, I know problems are uncomputable. We have a list of millions of them by now. Starting from Alan Turing, these are uncomputable problems. Just because I solve one instance of an uncomputable problem doesn't mean that I can solve it in general. Okay? Let me give you a very simple example of this. Diophantine equations, which are just equations with integer coordinates, polynomial equations, but you're looking for integer solutions. All right? Being able to tell whether a Diophantine equation has an integer solution is uncomputable. That's a theorem, right? But we know that Fermat's last theorem doesn't have any solutions. There we have solved the problem. Okay, but just because we solved that one problem, which is infinitely many cases, sub-cases, still, we can't say that in general human beings can solve an uncomputable problem. So
even this one is not a perfect proof, because when you flip it, it's not a Euclidean plane anymore.
Yeah.
You need another dimension to flip it.
So let me give you, for example, there were these BBC news that bees solve the traveling salesman problem. Well, they solve a particular instance of it. They can't solve it in general, and the theorem doesn't say that particular cases are not solvable. So there I disagree with Penrose.
I'd like to say that what differs just from machines. I think that consciousness is basically randomness. As computer, no matter what you can do, you will not be able to make an algorithm for randomness. You could say roll the die, but that requires a human, but that requires a physical action. As for an algorithm, you can't say to make randomness, pick a number. You need an algorithm for that, and then that's not random anymore.
You could use quantum mechanics to simulate randomness, right? You could have, quantum mechanics allows randomness, right?
Yes, but quantum mechanics is not. You cannot compute quantum mechanics. Quantum mechanics has to be observed, or shown to a computer.
Yeah. So, strictly speaking, a quantum computer can introduce randomness. It does have that capacity. So there must be something else about us.
Yes, I would like to also ask, since these tiles were found using hexagonal grids that cover the Euclidean plate, can we say that every single tessellation is the same, almost? Made of the same triangles or hexagons or whatever?
Yeah. So you could take each one of them and convert them into pentagons. We saw that they were made out of pentagons.
But does that work for every tessellation?
Of these things?
No, every tessellation, every aperiodic and periodic tessellation.
That's a very difficult question. I would have to search the literature. If the answer to your question is known, it will be a very deep theorem, I would think. It's a very deep question. Yeah.
An educationist, I just wanted to know where I can download these 3D from, if there is any resource you can just share it with us.
I will share the resources on the Facebook page because I was just so bogged down with my programming that, usually I give Nayyar references which he puts on my announcements, but I'll collect them for you.
For Penrose tiling, I actually use atishb.com. There is a online resource where I can actually generate these designs by changing the size, by changing the numbers. And so you were actually making your own animations, probably coding it. So is there any resource for designing this?
Whatever resource I've seen, it's limited, in the sense that it will allow you to do, change parameters and see things, right? But it wouldn't allow you to, bring them together and like the kind of fancy things I was doing. Yeah. So they sort of limit your use if it's. But I'll find other resources and put them up.
Hello, sir. I was a little late. I will watch the animations you showed. I'm not a mathematician, or I was never interested in mathematics due to our teachers. You can say this is the first class of mathematics that actually interests me. So I'm a student of social science. I will just say that these things should be introduced at college level or school level. These two children over there, they are very interested in this thing. We will research on it. And before when we are in college or school, we should have known that this maths is also a beautiful subject.
Yeah. I think that the aesthetic side of mathematics has to be introduced early, but for that, teachers have to work very hard. It's very difficult to convince people of that if you can't excite them.
But that what make a teacher a real teacher.
Yeah. That's it. Well, I don't know. It's a difficult job to be a good teacher. Very difficult, almost impossible. It's like impossible to be a good parent, impossible to be a good teacher. You can always improve.
I just wanted to comment on the thing that machines are better than humans. Well, there certainly not. There are limitations, as you said that mathematics proves that there are certain limitations. There are certain instances in which things are better than, in which cases are proved. There are some instances which are proved and some are not going to be proved. Similarly, the thing that ChatGPT, I am a student of computer science, and I just play with it. I do prompt engineering with it, and it fails if you just try to ask a complex question in a very complex manner. Like you just put forward that this is you just say I just want to share one example. There are multiple examples which I have just you say that 0 degree Fahrenheit and 32 degree Fahrenheit plus 32 degree Fahrenheit is equals to 64 degree Fahrenheit. Prove it, and it will prove it. It will prove you wrong. Well, if you just do this other mathematic formulas which I have seen, they say that it is possible that if you add temperatures, they can be added. But it says that 32 plus 32 degree Fahrenheit is not equal to 64 degree Fahrenheit. Similarly, 0 degree Celsius plus 0 degree Celsius is not equal to 64 degree Fahrenheit. There are certain limitations and it cannot tackle complex problems, and certain limitations have been put into it so that the product, so that
So can we just cut it down?
there are certain limitations. The crux of the problem is that there are certain limitations because we, the human, are the coders.
Anyway, there was one sentence of Chomsky which I really wanted to say. He was asked, can machines think, right? And he said, do submarines know how to swim? I mean, it's...
Airplanes fly.
Do the planes know how to fly? I mean, would you run, a race with a car? It's to me, these are meaningless questions. And it's just, I mean, they can be interesting, but there are... I mean, I don't find them only mildly interesting. Shall we come to your question now?
So I just want to make a final comment about the discussion about Penrose. You made an excellent point about like humans can find instances of an uncomputable problem, but they can't solve it generally. To prove that the human brain was incomputable, we would have to demonstrate that we can derive all cases somehow, and that would perhaps require an algorithm, and maybe we could have programmed that algorithm into a computer. So it's fundamentally an unanswerable question. So Penrose's argument is definitely flawed. But the main argument Penrose used in his book to prove that the human brain is incomputable was using Gödel's theorem, actually. For example, if we take if Gödel's theorems prove that if you take any system of axioms, there are statements that are true within that axiom system that cannot be proved from those axioms.
Agree.
So, for example, if you can construct a Gödel sentence out of any system of axioms. That Gödel sentence, we can demonstrate that to be true as humans. But if you were the system itself, you couldn't have reached the truth of that statement by any means. So he uses that statement to say that, look, we humans can apprehend the truth of that Gödel sentence, but the system itself can't reach the truth of that Gödel sentence. So therefore, we know more than the axiomatic system. So we will always know more than any computer system as well, if the computer system has axioms behind it, if it's running on an axiomatic system. But that is also flawed, because this argument only proves that you are more powerful than that particular axiomatic system. Once again, to prove that the human brain was incomputable, we would first have to we would first have to discover what are Gödel sentences. For that, we would have to discover what our axioms are. We don't even know what our axioms are on which our brain is running, which axiomatic system our brain is running on. And secondly, we have to find our Gödel sentence. And then we have to prove that we can prove the truth of that Gödel sentence. So Penrose's arguments rest on really shaky grounds. And almost no logician, no philosopher agrees with his arguments. Only a few, small minority. So almost nobody who is in the business of logic and philosophy agrees with Penrose. And actually, Penrose was not the first one to make this argument. This argument was actually made by a British philosopher and logician who was based at Oxford, whose name was Lucas. He gave this argument in the 1960s. He was also motivated by the fact that humans should be somehow more than machines. So that it's kind of like a motivated reasoning. People come from different backgrounds and different philosophies of life. Some people tend to think that humans are fundamentally more creative. They have a different kind of metaphysical essence. And if you know a bit of mathematics, you might use mathematics to prove your prior assumptions. So he gave that argument in 1960, and it was almost immediately refuted by logicians, and Penrose came along later. And it's a very rare case of such a prominent intellectual backing a discredited argument. So it's this argument is famous only because it has Penrose's name associated with it. If you only take it on the argument itself, it has almost no strength to it. So that was my comment on this. So it's not really the case at all that the human brain is incomputable. It's most probably computable and can be simulated. But then there are other questions like Searle's Chinese room, etc. Those are more. But then the question that I asked you during the lecture.
Yeah. So let me
about
just
the-
answer that. That was a very nice question, and certainly. So there is a. Yeah. So I'll. So the question was, if I show you that we can cover arbitrary large pieces of the Euclidean plane, does that prove that I can cover the entire plane? Okay, if I had infinitely many pieces. So for that, there's something called Koenig, and I have to pronounce him right because my advisor was Hungarian. If we couldn't pronounce a Hungarian name wrong. So this is called the Koenig tree lemma. Okay, and it says that suppose you have a tree. Okay, so a tree is just some kind of a hierarchical structure, right? Which has two properties. Number one is that it has infinitely many nodes. Okay. So A is this, B is that every degree is the number of children, right? Degree is finite. Okay? Then Koenig concludes from here that then there is an infinite branch in it. Okay? All right, so this is a combinatorial lemma. The proof is not difficult, but most of the time people give a wrong proof of it. So it's one of those theorems which is true, but people fall in a trap. Now, what happens is let's say you can cover arbitrary large areas with certain tiles. Okay? All right? Arbitrary large areas with certain tiles. Then you make a tree. Okay? At the top you put 0 tiles. Okay? At the first level you put all possible ways of extending these 0 tiles to 1 tiles. Okay? At the next level you put all possible ways of extending this by surrounding them with more tiles. All right? So because you can cover arbitrary large areas, that tells you that this tree must be infinite. So the first condition is satisfied. And the second condition is once you have made an area, you can extend it only in finitely many ways. All right? So the second property is satisfied. Okay? So Koenig tree's lemma says that there is an infinite branch. Okay? Now if you had foresight, you could follow this infinite branch. Okay, but we don't. So there is a way to cover the entire plane, but we don't know how.
Yes, or we can restate it as follows, that instead of saying that there is only a single tiling that can tile the infinite plane, instead of that we can say that for any finite area that you choose, there exists a tiling that can cover that finite area.
Yeah.
So from that you can infer that
Yes.
for any area you choose, there will always exist a tiling
To
that
extend it.
will aperiodically cover that plane.
Yeah.
So that proves the infinite case as well, I think, by induction.
Yeah.
And so on.
So actually you are re-arguing the Koenig tree lemma. This is distilled.
Came to my mind after I asked the question. So.
Yeah, this is distilled in here. Okay, thank you.